the occurrence of lightning in major cities, major metropolitan areas, one of which you live in, and to discuss this complex interaction between a city and the atmosphere, and how we can find the fingerprints of this effect almost very clearly because of this imposed, I would say, secession during COVID-19 lockdowns. We will discuss this because it has a major effect on how cities interact with the atmosphere and as a consequence with lightning. So cities, you know, you live in one of the largest metropolitan areas in the world. I believe 20 million people. How many in larger area of Mumbai? Maybe it's the fourth or fifth largest city in the world, following Tokyo, Beijing, Shanghai, maybe Delhi, Sao Paulo, other major areas, and it's huge. I mean, you know, my country, Israel, is 9 million people. Your city is more the entire population of my country. So it's a huge country, it's a huge city, and of course, what is typical of major large metropolitan area is the built area. They are made of concrete and stone and asphalt, and they are in irregular shapes. They have very tall buildings, high-rise buildings, and irregular shapes, streets, avenues, forming what we call urban canyons, like maybe not so much so in Mumbai, but in New York City or in those large American towns where you have high-rise buildings. They form like a canyon, all those avenues. It's just like a canyon where the wind is streamed inside. So many interesting interactions occur between a city and the air that flows into the city or above the city and downwind away from the city. So the effect may be local above the city, but they can also be felt at very large distances away from the city. So the city has a unique topography. It is made of materials which are different from the natural environment. And last but not least, cities emit stuff into the air. You know that. We call it pollution, but it's not only pollution. It's gases and even paint peeling off the walls. It's minerals. It's us living in those cities emitting all sorts of emissions into the air. So cities are definitely areas where there's a difference between the natural environment and the human-made environment. And one of the aspects that I took interest in is the interaction that leads to lightning. As we've learned yesterday, lightning is generated in specific types of clouds, very strong, massive CB, cumulonimbus clouds, and those clouds in turn are affected by the local atmospheric conditions. So there's obviously interaction between cities and lightning, and there are many evidence for that. Many research papers published, I would say hundreds, and I picked just a few, and we will focus on them, and we will try and assess how strong is the effect. And I'm going to show you lightning obtained from different lightning detection systems. I didn't talk about lightning detection systems yet, although I mentioned them yesterday when we talked about, you remember, the blue points on the satellite image from the lightning location, the global network. We will discuss this later, maybe today, this afternoon, or tomorrow. But anyway, when we map the incidence of lightning in a certain area, we can easily draw a map of where lightning is most likely to occur and occurs. And we build a database over a long period and accumulate data and create those maps. So, for example, this is from a paper published a couple of years ago by my colleague Oscar Pinto from São Paulo in Brazil. São Paulo is a huge metropolitan area. I think it competes with Mumbai in terms of the sheer vast area it covers. And what you see here is like lightning maps from 3 years, 2004, 5, and 6. And what you notice, so the color is the concentration of lightning per square kilometer per season or per month. You don't see the numbers, but it doesn't matter. It's just more of a qualitative impression that where the circle is the area where São Paulo is located. And what you can clearly see that above this major city, there is a considerable increase in the amount of lightning compared to the environment. So most of this area, not such a high density, but there's a maximum here and maybe also here. Come back. And also, so same here and same here. Different years, different geographical distribution of the lightning, but certainly it's easily observable that lightning is more frequent above the city. I should give a cautionary note here and say that lightning detection systems are always improving with time. New software, new detectors, maybe additional antenna to detect more and more lightning. So there may be a bias that tells us, yes, in 25 there were more lightning than in 2004, but that's not because there were actually more lightning. It may be an effect of better detection. We improve the system, so we see more lightning. So is it a real signal, or is it a biased data that kind of leads us to maybe jump into conclusions which are not necessarily true? So that's always in the back of our mind, that if you want to compare apples to apples, be sure you're not putting some oranges inside. So you have to calibrate and assess the detection efficiency. Was this a real signal? Well, in this paper, it is a real signal. We see it continuously. Every year, during warm season, lightning, you can see this maximum here above the city. And it's not unique to São Paulo. This is a map from Houston. So this is the coast, the Gulf Coast, southern United States, the Gulf of Mexico. Houston is a huge city. I was there when I was working with NASA in the Johnson Space Flight Center, and to drive from one part of the city to the other, it's not unlike, it's 1 hour on a free highway. It's huge. Like, you know what they say, in Texas everything is big. It's a huge country, and what you can see here is that this is the lightning map, lightning flash density per kilometer square per year, and you can see that above the city and neighboring cities there's a conspicuous maximum. So the city intensifies the incidence of lightning, and we will spend some time thinking why this is so. Okay? This is from a research in South Korea. So this is the South Korean peninsula, and this group published a lightning map for the entire country, and you can see several maxima. So they're not equally distributed, the lightning. It's not the same density everywhere, but you can see that there are some conspicuous maxima in certain areas. And coincidentally, these are the areas of the major cities in South Korea. So we see this pattern reappearing in many, many large areas where there are big cities that interact with the atmosphere and as a consequence lead to the enhancement of lightning. This is an interesting study from Atlanta in Georgia, the US. Atlanta is a city that grew very rapidly from the 1970s and early 80s until present day. And what they did was show this rapid growth of the city. And as a result of this urban expansion, the number of lightning around this built area also increased dramatically. So it's not just a matter of comparing every year the detection efficiency of our system, but it's also considering that cities are not stationary. They are expanding. Population is growing, more buildings are built. So there is, I would say, an evolution of the city, as if you want to call it an organism, like a meta-organism. It grows all the time. It expands, it changes, and so the interactions become more and more complex. And so, just as a headline, cities affect the atmosphere and enhance the amount of lightning over the city. And I will try and figure out why this is so. So, one of the first clues that we get is, this is a paper recently published for the lightning enhancement above the Beijing metropolitan area. Beijing, probably you haven't been to that city. I've been there a couple of times. China is amazing, and Beijing as I would say, the capital of this country is an amazing urban, I dare to say, monster, let's say dragon, famous from Chinese culture. It's so large that, and you drive from side to side, enormous urban area. And when you fly above it, you see it's endless. Buildings and buildings and buildings. Millions of people, millions of cars every day. And, of course, trains, industry, power stations, the airports, all those human activities, what do? They emit aerosols into the air, particles. And as we discussed yesterday and on Tuesday, there is an interaction between particles and ions which affect the formation of clouds and by inference affect the generation of electricity and maybe lightning inside thunderstorms. And you can see clearly that this is Beijing, and this is the lightning map of around the city, and you can see clear maximum above the city of Beijing. And why is this occurring? This is 8 years of data, normalizing the fact that the Chinese lightning detection network improved over time, so it counts more lightning, but then they can do this normalization and compute a baseline, and still the signal is there. So you see this is lightning enhancement around other areas, and clearly Beijing shows a maximum, but other cities as well. And the effect is not only limited to the city itself, it spreads around. Because obviously you know that pollution does not stay in place. Aerosols are not just emitted and wait above the city. They are being carried away, sometimes very large distances away from the emission point into the air, hundreds of kilometers away. So the effect of pollution emitted from a major city on the atmosphere is not restricted to the city itself, but shows a more regional effect of lightning enhancement. And what they did was they wanted to look very carefully. I'm not sure you can see this, but these are different types of pollution, PM10, PM2.5. These are aerosol size particles, NO2 and SO2. Those two pollutants, gases, are related, of course, to mostly transportation, cars, and there's a cycle. These are days. I believe this is the summer of 2014. So this is June, 15th of June, 1st of July, 15th of July, August, mid-August, and September 1st. And what you can see is that the red peaks are days where there were lightning. So there's not always lightning. Lightning comes and goes, as we know. But notice this, that we see this periodicity in aerosol concentration, and sometimes it coincides with lightning. So the fact that the city emits a lot of aerosol particles sometimes enhances the amount of lightning in that specific area. And of course, gases are also important because we know from atmospheric chemistry that sometimes under specific conditions, gases turn into aerosol particles. We call it photochemical conversion, or GPC, gas to particle conversion, due to the interaction in the presence of sunlight, water vapor, and those gases. Sometimes you can just create aerosol particles, PM1, which means 1 micron in size, or PM2.5, 2.5 microns, just by the release of gases and the chemical interaction they are going through. So this is maybe evidence for the periodicity of aerosol production and how it affects the generation of lightning. Not only in Beijing. This is a study recently published which deals with what we call the urban lightning effect. It got an acronym, a ULE. What I found when I was working in the US, that Americans in general like to have abbreviation. So they give acronyms to anything. When actually we started working at NASA, they were talking regularly in acronyms, and we didn't understand what they were saying. So they printed a dictionary for us because they were so technical and space mission oriented. So they used many abbreviations and acronyms, and we had to study everything because it's like a language. It's called like NASA-ish language, not gibberish, but kind of, you have to follow it. And so now this group introduced this ULE, urban lightning effect, which describes of large urban areas to augment the lightning, what they call proximal flash occurrence, either above the city or in the proximity of the city. So how anthropogenic effect occurs? So two effects. One is due to the sheer effect of the geometry of the city. The city, compared to its natural surroundings, is more rough. So we call it surface roughness or friction, if you wish. So airflow is disturbed, and this causes what we call convergence. The air is not flowing smoothly like it does above the sea or above woods or flat areas. So this creates conversion and lift. So air is being lifted above the city because of the surface roughness and the convergence, and because the city is normally hotter than its surroundings. I'm sure you've heard about this. It's called the urban heat island effect, the UHI, another acronym. But the urban heat island is well known. Every large city builds its, I would say, canopy of heat. And this is immediately felt if you go outside of the city, temperature drops by 2 degrees on average. Just the sheer structure of concrete, asphalt, dark surfaces which absorb solar radiation because of their low albedo, and they emit a huge amount of infrared. If you look at the city from space with an infrared sensor, you would see a big conspicuous area of heat. So cities generate heat and create upward motion in the air, which of course encourages the formation of clouds, as we learned on Tuesday. The second effect is what was hinted for in the first slide in China, is the modification of the microphysical conditions. You infuse the atmosphere with more and more particles that actually affect microphysical conditions, driving cloud electrification by man-made aerosols. So we are changing not only the dynamics of the clouds, but also their microphysical state and their potential to produce lightning. So this group took data from a new satellite that was launched 4 years ago. It's called the Global Lightning Mapper. It's a geostationary satellite. You know what geostationary satellites are? So let me just give you a brief kind of description. There are two types of satellites. Low Earth orbit, which are around 800 or 1,000 kilometers, and they orbit the Earth at a low orbit, which is usually 90 minutes, every hour and a half, a full rotation of the planet. Actually, they are in a constant orbit in space. The Earth rotates below them because it's the law of inertia. You just launch it into space and there's no friction and there's an energy, so they don't almost never lose energy, and they just keep on flying in the same orbit you intended. And the Earth rotates below this orbit. So those are polar orbiting, or if the inclination of the orbit is tilted, so they are orbiting us in a slanted orbit. Geostationary satellites are located at much higher altitude, approximately 36,000 compared to 1,000 of low Earth orbit. 36,000 kilometers means that the satellite rotates around the Earth in the same rotation speed as the Earth revolves around its axis. So actually, they are always looking at the same area. So they are rotating with the planet, okay? So they complete one revolution every 24 hours, not every 90 minutes. So geostationary satellites are able to cover, although from a very large distance, the entire Earth or specific areas of the Earth continuously. Because low Earth orbit satellite, they go every 90 minutes, but then they go over a different part because the Earth already rotated. So the revisit time is twice a day. But geostationary satellites, they look all the time on the same part of the Earth, and they are used for weather monitoring, of course, meteorology, and for communication. These are the major satellite communication-based that are geostationary, and since it's a specific altitude, it's an international issue because everybody wants to have satellite at that altitude, and somebody has to regulate. And although space is big, still, if you have too many objects in space, there may be interferences and problems and even collisions. So geostationary satellites are regulated by an international body. There's a commission. Anyway, to get back to this research, what they did was take a satellite that was launched by NOAA. NOAA is an acronym for National Oceanic and Atmospheric Administration. It's the body in the US, the government agency in the US that is responsible for monitoring the atmosphere and the oceans. NASA deals with similar tasks, but it's mostly space-oriented. NOAA is Earth-oriented. So this geostationary satellite looked at 3 cities in the US. Atlanta, as we discussed before, it's a city that grew up really rapidly and now became one of the US largest cities. A rather medium-sized American city named Greenville, and Charlotte, Indiana. So these are neighboring cities, and what they are looking for, A, B, and C, is how much lightning occurs around each of those cities. And you can see this is Atlanta, this is Greenville, and this is Charlotte. And each column shows different parameters that were remotely sensed by the satellite. So the satellite has a very sensitive camera that can capture lightning light. It sees the light of the late night of the flash. Like today after lunch when we do the assignment, you will see it with your own eyes, how lightning looks from space. I will give you real data, but not from 36,000 kilometers, rather from the International Space Station, 420 kilometers. So closer means that the lightning is much brighter, and you see it occupies a larger area in the image. But if you're looking from far away, then the resolution is rather coarse, and so each square is a different is a larger area. And you can see that around those cities you have an enhancement of lightning, continuous enhancement. This is the flash rate density, which means how much lightning occurs per unit of time. This is how many days per year do you have lightning, and what is the average number of flashes per day. Okay, so you take the total number of lightning, divide it by the total days that there were thunderstorms. Remember, yesterday I mentioned the term thunder day. A thunder day is a day when you heard the thunder, which means there was thunderstorm somewhere around you. By the way, most humans, the hearing that we are dependent upon, we hear thunder from a range of about 20 kilometers. Okay? So we will discuss soon lightning safety issues. It means that if you hear thunder, lightning is closer than 20 kilometers away from you, and you should probably be careful. But we'll get to that. So, flash rate density, number of days where there was lightning, thunder days, and this is the flashes per day. And you can see that around major cities you can see the enhancement. Although I should confess it's not as clear a signal as one would have expected. There is an enhancement downwind from the city, not directly above it, but the effect is being drifted outside of the city into the rural area, because all the pollution, all the heat is carried with the clouds and with atmospheric motion. And so when they put those 3 cities side by side, Atlanta, Greenville, and Charlotte, there's a complex structure of lightning distribution. The table shows how the cities increased in population and how this expansion of the urban area manifested itself in a change in the total amount of lightning through the years. So this is a comparison between 2010 and 2019, a decade of data. So, for example, Atlanta grew from 5.3 million to 6 million. Charlotte from 2.2 to 2.6, and Greenville from 1.1 to 1.2 million. Still, not two small cities. I mean, of course, compared to Mumbai, they're still not that large, but so the increase in population in Atlanta was almost 14%, and in Charlotte 17%. And when they look at the percentage of lightning, you see an increase in all parameters related to this expansion, urban expansion. So there is a flash rate density increase which manifests itself in all three urban areas, some places more than the others, but definitely the fact that cities, as I mentioned, are evolving entities makes this interaction more complex and evolves with time. So it's not that we have a constant enhancement factor that we would say, okay, above this part of the city, you can expect that enhancement factor. No, there's nothing constant. It changes from year to year, and it's a complex kind of process because nature itself is not constant. One rainy season is not like another rainy season. Like, I looked at the newspaper and I saw that in Mumbai, this was the driest September in 5 years. They looked at the data. It was rainy, but not as rainy as 6 years ago. So some change is occurring. So moving from the US to Tehran in Iran, different regime, different size of city. While those American cities are located on plains and a rather flat area of the United States, so no conspicuous mountain ranges, Tehran is located in a basin. It's surrounded by chains of high mountains, and this research looked at the interaction between atmospheric pollution and CG lightning, CG cloud to ground. So their system, unlike the satellite-based system, was only able to detect cloud to ground flashes. Satellite system, they see the light. The light comes from either cloud to ground or intra-cloud, as we discussed, so they cannot tell the difference. But their data is quite limited only to cloud to ground, which is also, of course, very important issue. So what they did was zoom in around several specific locations in the metropolitan area of Tehran, where they had air pollution monitoring stations, because they wanted to look for relationships between the concentrations of pollutants and the number of lightning close to that area. And what they found was, this is the concentration of PM10 particles with a diameter larger than 10 microns, and this is the flash number. And for several years of data, they were using the Woolen network. So it's not a local network, it's a global network, the one that we discussed yesterday, and I will expand a little more today. And what they see is, I wouldn't say a very strong correlation. You see R is just 0.5. So it's not strong, but still there is a tendency. When we increase the amount of pollution, there is a conspicuous increase in the amount of cloud-to-ground lightning. Okay, so same signal, different relationship, but philosophically speaking, it's the same effect. Okay? So they were looking just for the microphysical effect. They were not discussing the dynamics, the convergence and the roughness and the uplift that the city causes, but they were just looking at one parameter, and they published this paper, and it's a good work. Now, how do we define the quality of air that we breathe? So, it's directly related to the concentration of particles and gases in the air, and there's a general kind of, I would say, language or metrics, if you wish, that is called the AQI, another acronym, Air Quality Index. Air Quality Index is measuring not the concentration in number of particles, but rather the collective weight. So it's as if you are collecting all the particles, putting them on a very sensitive scale and measuring what is the mass, the total mass, suspended in the air. Okay? There are several techniques of doing that and several ways of measuring it, and so these are WHO, World Health Organization standards. These are the old ones, these are the new ones, and you can see that there is rough definitions of categories when the air that we breathe is good, moderate, unhealthy for specific groups, unhealthy for everyone, very unhealthy, and hazardous, actually dangerous. So you probably know this, and if you don't, you may want to use it. You can install an app on your mobile that will tell you what is the AQI, the Air Quality Index, in the place you're located at. It uses your GPS location and connects to a network of sensors that is deployed. Maybe we will visit the website in a second. And then you can get the data in an hourly resolution, and in some countries you can get it in real time. Not the hourly average, but what is the value right now? And I give this to my students as an assignment to compare what is reported on the web through those apps and actually to do a direct measurement. So I bought air quality sensors. They're not very expensive, maybe $10, $15, and I give it to my students, and they go out and measure the air quality directly with their device, and then they compare it to what's reported on the app. And it's a good exercise because it helps you validate or maybe invalidate what is being reported. You may think, these guys know what they're reporting, it's okay. Air quality is fine, I should go out jogging or doing whatever I need. But then if you do the actual measurement, you discover that they're maybe sometimes way off. So they report moderate, but it's actually unhealthy. And I had one student, she graduated and moved to work in a volunteer organization, a Jewish organization in a large city in China. I think it was Guangzhou. And so she calls me one day and said, Yoav, the local authorities say that the air quality is good. I want to go jogging in the park. Should I go or should I not go? She remembered what we were discussing in class. And she had no device, so she had to trust. But I said, the Chinese authorities sometimes, maybe on purpose, maybe just because it's not calibrated, deviate from the true value, and usually on the good side, because they don't want to show how bad the quality of air in China is. So be careful. Don't do it. Don't go out. Even if it says that it's moderate, probably it's much worse. Don't go out. But she paid no attention, and she went out running, and then she was ill for 2 weeks. She got lung disease, coughed a lot, and I told her that let that be a lesson to you, that if there is an official data, you can trust it, but a little suspicion won't hurt you. Maybe check it if you are able to with your own system, your own device. And now there are some startup companies that actually want to make each and every cell phone as a measuring unit, which will of course enhance the quality of data that we have, and then we can judge what is the true value of the AQI. So how is AQI related to lighting and to lighting enhancement above cities? There's a direct, obvious relationship because it tells us how much particles are suspended in the air. So this is how it looks like, okay? This is from Delhi, not from this day, but you can go online on your mobile phone and check the aqi.org, or I think aqi.net, and you can see the data, and the data is continuous, and it's being updated, and it has many parameters. So this is a specific station, Anand Vihar, Delhi real-time air. So the air quality AQI value is 180. It's unhealthy. And you can see that there are other parameters that are being reported. PM2.5, PM10, ozone, NO2, SO2, carbon monoxide, and then the usual meteorological parameters, temperature, pressure, humidity, and wind. And you can see that there are cycles. So this is every day. This is Saturday, 6 a.m., noon, evening, Sunday. There's a pattern, okay, for the pollution. Why is there a pattern for the pollution? Like a cycle? Traffic, yes, obviously. Human activity is changing throughout the day and is manifested in the amount of pollution that is emitted. And we'll get back to that shortly. So you already see, just from observing the data, that there is a pattern. And you can actually go to high resolution and focus on a specific station and get a lot of data if you want to analyze. Okay? And just as I think I mentioned it yesterday, this is from 2019, from very short time after Diwali. The pollution in central India was enormous. And this guy reported on Twitter that Delhi has turned into a gas chamber. So people were getting sick because the high level of pollution due to these circumstances of specific meteorological conditions and a huge amount of emission of biomass burning and those fireworks and bonfires, and everything converged together to create this. Look at the color map. PM 2.5 air pollution concentration. Huge area. Mumbai is slightly less affected, but central India and certainly the east coast, highly polluted. And now, by a strange turn of events, as we discussed, something happened. And I took this from The Economist. I think it's a brilliant, really, just see how simple, clever, and you get it. This is what an ingenious copywriter, like a graphic designer, it was on the front page and everybody knew what he was talking about. So COVID-19, had a remarkable effect on human activities. Obviously, you felt it, everybody did. But as atmospheric scientists, it allowed us an unparalleled chance to observe the true value of human influence on the atmosphere. Because suddenly you took out almost 90% of human emissions and anthropogenic effects because you shut down everything. And the economy almost ground to a standstill. Let me show you some examples. This is the number of flights in China before the lockdown, just a snapshot of any day. This is January 23rd, 2020, just before lockdown was announced in China. 12,814 flights per day in China. And this is February 13th, after lockdown was imposed. And in China it was imposed, believe me, they did it in a very strict, compulsory manner. 1,600 flights. So we reduced the amount of emissions from airplanes, and by inference from trains, cars, ships, everything, by a factor of 10. Okay? In a single 2 weeks, in 2 weeks' time. Quite amazing. And if you look at the level of pollution as it was remotely sensed by satellite sensors, so this is NO2 directly related to traffic. Okay? So this is Wuhan area. This is data from 2019, before COVID. Same period, 2020. Lockdown. Everything vanishes completely. It's like you force this kind of curfew on the population. No cars on the roads, no gas are emitted, no particles are formed, nothing. The air becomes almost pristine, clean. This is NO2 in the great area of China. So this is Beijing metropolitan area, right? Blue sky. When I visited Beijing several times, I had a collaboration with a colleague, Professor Qi from the Chinese Academy of Sciences that's in Beijing. And I visited there several times for mutual research. By the way, we were studying the effects of cities on lightning. We were comparing Tel Aviv and Beijing. Beijing, 20 million, Tel Aviv, 1 million. But still interesting. So when first time I was there, the sky was always yellow or gray. And my colleagues told me that jokingly people call Beijing Grayjing because you never see blue sky. Grayjing, it's always polluted. Millions of cars. And until several years ago, they were burning diesel fuel, so highly polluting fuel. So Beijing was polluted like hell. And then they changed the regulation and slowly and gradually imposed new rules on emissions. And there were few days that you could actually see blue sky. And in 2016, when I was there last time, 2018, it so happened that there were some blue days that you can see blue sky. And back then there was a joke that when the period was such that Beijing was still very polluted and gray, there was supposed to be a big international meeting in Beijing, and the authorities, the Chinese Communist Party, was very worried that people would be biased negatively against the Republic of China. And it was before the Olympic Games of 2008. So China was really worried about getting the Olympics. And so what they did was, before all these international delegations arrived in Beijing, they ordered all power stations that were working on coal to shut down. All the diesel emissions from buses, trucks, and trains shut down. So that meeting took place. It was called OPEC, O-P-E-C, Organization for I don't remember what, in China. Anyway, so all those ministers came from all over the world. It was 2007, 2006. And suddenly for 1 week, blue skies above Beijing, and that jokingly was referred to as OPEC Blue, because it was only those few days that those ministers arrived that the Chinese government was so strict on pollution emission that the sky turned blue. And after they left, it immediately turned gray again. And it took them another 10 or 15 years to actually reform their entire standards of air pollution. And you know why? For the simple reason that if you breathe unhealthy air for long periods of time, eventually you will get sick, you will not show up for work, economic production will go down, and that will hurt the economy of the country. So it was in their own best interest to improve air quality. And lo and behold, when this COVID-19 lockdown occurred, immediately all the air in China cleared in an instant. But not only in China. So this is northern Italy from a satellite. This is a European Space Agency satellite called Sentinel-5, and it has a sensor to monitor the concentration of NO2. This is March 2019, a year before COVID. Northern Italy is the major industrial hub of Italy. It's the big cities, Turin, Milan, the car manufacturing industry, the fashion industry, everything that is branded Italian, and probably you know this, high quality, is located here in what we call the Po Valley, named after the river Po. So this is 2019. And this is the same period after COVID struck Italy. And Italy was struck bad, really bad. They were coping with an enormous amount of infection, and they had to shut down the entire country completely. And you can see how the concentration turned, I wouldn't say to zero like in China. Probably some activity remained. They were not as strict as the Communist Party in China. But this is interesting. You can see. And for those of you who are interested in geopolitics or in the larger scale of things, it tells you that you can actually, from an objective space platform, identify economic processes down on Earth without being there, just remotely sense. So northern Italy, completely cleaned. And even here, I like this picture. This is a famous monument in Delhi. And this is before lockdown, and this is after lockdown. Sky became clear. I read somewhere in the paper that actually people were able to see the Himalaya from Delhi for the first time in 25 years. The sky was clear. So obviously lockdown and the shutting of traffic and industry, and because of that, not as much power needed to be generated. Not if the economy is stopping, you don't need that much power generation. So everything came down to a halt. and we saw large improvement in air quality and the diminishing amount of particles in the air. Now, was this manifested in the amount of lightning? Yes. And this is from a recent paper in Calcutta, other side of the country from here, but they were comparing what happened from this period where Calcutta was under lockdown, March, to May of 2020, decreasing all the amount of pollutant, and they were looking at the amount of lightning above the larger urban area of Calcutta, and you can see, although there are daily variation, there is strong decrease. Very clear and pronounced signal that when you shut down particle emission, leaving everything the same, meteorology did not change. The properties of the clouds were modified, and there was a decrease. The aerosol amount was decreased from between 40 to 68%. So not going to zero, but huge decrease in the amount of pollution, and the lightning decrease, on average, 50% less. That's a very clear signal. This is a human fingerprint that we see in the atmosphere. So we knew that we enhance lightning, but we can also decrease lightning by playing with the quality of the air. And it's not unique to India. It's everywhere. As we've seen, lightning enhancement is common in many, many areas around the world where you have large cities. And I showed you a few examples from Houston, from the US, from Brazil. And this is another example, a recent paper by Osmar Pinto, my colleague, and again looking at Sao Paulo, that went into lockdown as well. A short period, relatively from March 20 to April 2nd. And they compared two major urban areas, Sao Paulo and Belo Horizonte. Belo Horizonte is a large city in Brazil, and today you will get to know it because we will look at video from the space station above that city of the thunderstorms right above Belo Horizonte, which is in the southern part of Brazil. And what they found was that indeed, so this is a lightning map, not so, that shows a very poor graphics. So this, come back. So this is Sao Paulo, Belo Horizonte. There are some lightning, but there is a decrease in the amount of lightning. They compared several years. This is the year of the lockdown. And there is a signal, but not as strong as, for example, in Calcutta or in other parts of the world. And they were not sure why this is so. So they wrote something uncommitted, like it's complex, we don't know, there is a decrease, but it's not 100% sure that it's because of the lockdown, and it's a very short period. It's just less than 1 month. So is it significant? They were leaving it open. But I chose to show you that when we do research and we expect something, we have an hypothesis, the results not always match what we expect. And it's for us to try and understand why didn't we see this as clearly as it was shown in India, 50% decrease in 2 months, and here almost nothing. In one city, not so significant decrease, and maybe the average intensity of the lightning was slightly increased, but not significantly so. So, not unequivocal effect everywhere in the world. Still, it tells us the story of how major cities affect lightning and how the human effect can be taken out by this lockdown. Okay, time for tea. Am I right? Do you like? Yeah, shall we have a tea break now? Or do you want me to continue? I think we'll take a break. So let's continue in 15 minutes. Okay? And we will stop at 11:30 because I have to go to the Vice Chancellor's office. So please be back in 15 minutes and then we'll continue. All right?